This week we're going to look a little bit more closely at rotational motion, and we're going to use some of the concepts that we've been using for linear motion to describe how things move when they're rotating. So let's start with an object that's rotating around an axis. So this, let's say it's a disk or something like that, rotating around an axis right there. And I can describe the motion of any point on this disk by how far it moves in an angle. And if it's moving in, uniform circular rotation here, we know it's got a velocity that's tangent to the edge of the circle. We'll call it the tangential velocity. We've already talked about the ideas of centripetal acceleration. But what we want to do is relate the motion of any point along this disk to its position as it goes around. Now, this entire solid object is going to rotate with a constant angular speed, right? So while the speed at the edge of the disk is going to change depending on the size of the disk, how fast it goes around, how many times it revolves as it goes around one full 360-degree rotation is going to stay fixed. Okay, so we can write down this angle here. That angle is our, you can consider that the position along this line of rotation. And then we can write down the angular velocity, which we use omega for that. And that's going to be a constant for anywhere on the disk. Now, if we change that angular velocity, we have an angular acceleration. And we can look at the exact same thing that we saw before when we plot these things for constant angular acceleration versus time, right? That's going to be a constant like that. And going from one point to another is just going to be the area under that curve, right? So we can say that the angular velocity at some final point, if we have an angular acceleration, is going to be equal to the initial angular velocity plus the angular acceleration times time, because this right here is just the area under that curve. That gives us a graph for angular velocity that's going to change with time. And just like we saw before with regular velocity, that's also going to be the area under this curve. So the angular position is going to be whatever the initial angular position was, plus the change in the position due to this contribution, so that's going to be my initial angular velocity times time, plus 1/2 alpha t squared, because that's going to be the area of this triangle right here. So you see we have the exact same equations for the change in the angle that we had for linear position. So I can just write those down. We have our final angular position is equal to the initial angular position plus the initial angular velocity times time plus 1/2 times the angular acceleration times time squared. And then our final angular velocity is just equal to that. And so these look just like our, if we remember, we had our linear position changed with respect to the velocity and the acceleration, and our linear velocity changed with the acceleration. So these look with the acceleration. So these look exactly the same. You're just putting in one variable in place of another. So there are no new equations to try and remember here. These just come out of the same graphs again. Now, let's see how these variables relate to the physical size of the object that's rotating. So if it has a radius, let's say r, right, and we imagine that there's a arc length s that is being swept out, then if we know the arc length are being swept out here, and we know the radius of this thing, we can write down the angle as being just s over r. Or another way to write that is that the arc distance is just the angle in radians times r. We can do the same thing with the angular velocity. The angular velocity is equal to the tangential velocity times r, or we can say that the tangential velocity is equal to the angular velocity divided by r. And then you can do the same thing with the tangential acceleration. That's going to be the change in acceleration along that's parallel or perpendicular to the disk there. That's just going to be equal to the angular acceleration divided by the distance. And then we have our regular centripetal acceleration that we talked about before, which is the tangential velocity squared over r. So this tells us how all of these variables are related to one another. Now the only other issue that we have here is that if a disk is changing its rotation, then it is experiencing both a force. If we have to change the rotation of this disk, we have to apply a force someplace, but the force is going into changing the rotation rate of this object, which means it's going into changing the kinetic energy of the object, but we're not pushing it to a higher velocity in a linear fashion. We're just rotating it up. So we have a couple of other concepts that we need to worry about as far as how the rotation of the disk is going to change. One of them is called the moment of inertia. The moment of inertia describes how difficult it is to change the rotation of an object. If you have a large moment of inertia, that means that it's very resistant to changes in its rotation. If you have a small moment of inertia, that means that it's relatively easy to change its rotation. And the moment of inertia, if you imagine if you've got an object, just a point source, or a point object that's some distance from some position of rotation and it's rotating around like that, the moment of inertia of that single point is just mr squared. So it's proportional to the mass and the distance squared away from whatever the point of rotation is. Now if I have another object like that, or another object like that, then I just add up the contribution to each one of those, so this becomes the sum of mr squared. And then depending on how the mass is distributed, if I have a solid object like a disk or a ball or a box or something like that, I have to do this sum of all the different components of this, and that will tell me how resistant this object is to changes in its motion. Now, if you can kind of see by this, though, that the more massive an object is, the harder it is going to be to rotate, but also the more compact it is. So if I have most of the mass oriented in the center, right, that's going to make it easier to rotate because this r is going to be relatively small. If I have the mass distributed around the edge, that's going to make it harder to rotate because the mass is distributed farther from the center. And that gives us an idea of how the moment of inertia is going to change with different objects. And you can see there's a table in your book that has the moments of inertia calculated for a number of different objects. So when we think about this concept of inertia, we've seen this before in terms of mass, right? We have, if you have an object of a given mass and you try to move it, the force is proportional to the mass times acceleration. In fact, it's equal to the mass times the acceleration. So there's an equivalent relationship for rotation. If I want to rotate something by, say, applying a force on the edge, so if I apply a force on the edge and I do it a certain distance r away from the center, that force applied at that distance is called a torque. And we usually denote that with this little tau here. And the torque is what's related to this angular acceleration. And in fact, the torque is equal to the moment of inertia times the angular acceleration. So you can see there's a very kind of a parallel thing here between a force applied to get something to accelerate versus the torque applied to get something to accelerate in its rotation. There's a very analogous formula also for energy. If you remember, for a point particle moving at a certain velocity, we had kinetic energy was equal to 1/2 mv squared. Well, for a rotating object, if I have a rotating object that's some mass distribution, the kinetic energy for a rotating object is 1/2 I omega squared. Okay, so again, very similar functional form, but the kinetic energy is going to be determined by the angular rotation and the distribution of mass. And then finally, if you remember when we had this concept of work, if we had a point source moved over, or point object moved over a distance, that the work was just the integral of the force dotted into the distance. Well, the work for a rotating object, since you can imagine that since we have the forces here applying to it, we're going to have the work is equal to the integral of the torque, the sum of the torques, times the angle through which those torques are causing a rotation. So if I'm applying a force on the edge of the disk and I apply that force for a given angle, then that's going to tell me how much work I've done on that disk. So again, you can see some parallels here between rotational motion and linear motion.